Welcome back. We're here on the campus of St. Michael's College with Ruth Fabian Fine, who's an associate professor of biology and neuroscience, talking about some really fascinating research that you have done. Tell us how spiders and neuroscience come into play.
So spiders have a nervous system that has very large neurons. And when I first discovered that these neurons are so clearly visible, I decided that I want to stick with this model system in order to investigate synaptic transmission. But then my spiders started to die of neurodegenerative diseases. And I thought, I'm losing my colony, so I better investigate what causes this. And so that's how we came to investigate neurodegeneration in spiders.
And what did you find?
And we found that there was a glial canal system that internalizes waste particles from the neurons, and that it was taken in by these glial canals. And in degenerating spiders, these glial canals ruptured and basically, like an industrial hoover, suck all of the content out of these neurons. And so the neurons completely depleted and died.
And so what implications then does this have when you look at humans?
So I looked at how neurons in degenerating spiders look like and compared them with what neurons in humans look like in Alzheimer's patients. And I discovered that they look the same. And then I teamed up with UVM Medical Center with Dr. DeWitt, and I said, can we look at whether there's a similar mechanism? And it took us no time to identify that there's a similar mechanism in the human system.
And so then why do we need to know this? What does it do to further the body of research around some of these neurodegenerative diseases?
Right. So you see, if you don't know an underlying mechanism, it is very hard to get treatment for it, right? So you basically tap in the dark. What am I going to do? But now that we have an underlying mechanism, that we know that there are some water pumps that are likely responsible for depleting those neurons, we now have a drug target. And that's what we're doing currently. We've now tested living brain cells with this drug target, and they indeed react to this blocker of this pump, and so it allows us to generate treatment.
And how far away, though, would we be talking about timeline-wise in making a treatment happen? I think that's always people say, "Ooh, it's exciting."
That is a very good question.
But it takes probably a while.
You know, science is it's often very difficult to get your idea accepted. So I think it all depends upon how long does it take the neuroscience community to accept the findings that I have. And I'm pretty convinced by those findings because this paper is only one paper of a lot of work that I've done that all supports my findings, including functional experiments. If the neuroscience community accepts this, my estimate from my experimental design is that within 3 years we can start clinical trials. That would be my estimate.
That is amazing as a timeline, honestly.
Yeah.
You've worked with a lot of undergrad students to make this research happen. I imagine you're continuing it in some way. Talk about what's next for it.
Yeah, so we have a lot of undergraduate students who work with us, and so they usually stay close and they want to continue in this field as well. And the next thing is now to do the functional work and the drug target work and confirm everything that we've found and make really clear that this is indeed the case. And so far it is all going really well.
I'm not a fan of spiders, but I am a fan of these findings. Thank you so much for sharing them with us.
Thank you.